Hi, I'm Yu. Today I will talk about near-linear size hypergraph cut sparsifiers. This is a joint work with Sanjeev and Ansh. Let's first define what is a cut sparsifier. Given a graph G, an epsilon cut sparsifier G' is a sparse subgraph that preserves all cut values in G within a factor of 1 plus or minus epsilon. Notice that the edge weights in the sparsifier are usually different from the edge weights in the original graph. For example, look at the picture below. In the original graph, there are 5 edges of weight 1 crossing the cut, but in the sparsifier, there is an edge of weight 2 and an edge weight of 3, and other edges didn't appear in the sparsifier. The cut size in both graphs are 5, so the cut size is preserved. Cut sparsifiers are usually used as a way for speeding up graph algorithms. For example, suppose there is a graph algorithm A, which solves a graph problem, and it runs slow in dense graphs. Then we might be able to speed up the algorithm using a cut sparsifier. Given a graph G, we can first compute the sparsifier graph G', and then run the algorithm A on G', which is fast because G' has less edges. Then for some problem, we can get an approximate solution since G' preserves all the cut value of G approximately. The quality of a sparsifier is the number of edges in it. There has been a lot of work studying the cut sparsifier problem. Benzo and Cargo issued a line of works. They prove that any graph has a cut sparsifier with order n log n edges. The best upper bound now is order n edges by Baston et al. This is also an upper bound for spectral sparsifier, which is a general case of cut sparsifier. Carlson et al. Proves that this bound is tight. They prove that any data structure that sketches cuts within 1 plus or minus epsilon factor requires order n log n bits. Note that it may appear that the lower bound is larger than the order n bound, but notice that each edge needs log n bit space to store, so this is not a contradiction with the upper bound. In this work, we consider the hypergraph cut sparsifier problem. In a hypergraph, an edge might contain more than 2 vertices. The value of a cut is the total weight of hyperedges crossing it. Given a hypergraph H, a cut sparsifier H' of H is a sparse hypergraph that preserves all cut size of H within a factor of 1 plus or minus epsilon. Let's look at this example. In the original graph, there are 4 hyperedges of weight 1 crossing the cut, while in the cut sparsifier, there are 2 hyperedges of weight 2 crossing the cut. Cut sizes in both hypergraphs are 4, and so the cut size is preserved. Before this work, the best upper bound of size of the hypergraph sparsifier is by Kogan and Kostgamma. They prove that any hypergraph has an epsilon sparsifier that contains order n times r plus log n hyperedges, where r is the maximum size of a hyperedge. Note that it is order n squared in general, since a hyperedge could have order n vertices. This is almost a factor n larger than the bound for normal graphs. In this work, we prove that any hypergraph has an epsilon cut sparsifier that contains order n log n hyperedges, which matches the same bound of normal graph within a log0 factor. This result also implies that there is an insertion-only single-pass streaming algorithm that computes an epsilon cut sparsifier with n log n hyperedges using order n squared bits of space. Note that a hyperedge may require order n bits to store since there might be exponential hyperedges in a hypergraph. Hypergraph cut sparsifier have a lot of applications. One of them is the application in SAT Sparsification, which is given by Kogan and Kostgamma. Any SAT formula phi on n variables can be represented by a hypergraph on 2n plus 1 vertices, such that for any assignment, there is a cut in the hypergraph whose size is equal to the number of satisfied courses. In particular, for any variable xi, we have 2 vertices which represents xi and xi bar. We also have a special vertex vf. For any course, we construct a hyperedge which contains each item in the course and also the special vertex VF. For example, for course x1 or x2 or x3 bar, we add a hyperedge which contains vx1, vx2, vx3 bar, and vf. For any assignment, we consider the cut which puts item assigned false with the special vertex f on one side and items which is assigned true on the other side. For example, for the assignment where x1, x2, x3, and x6 is false, and x4 and x5 is true, we put vx1, vx2, vx3, vx4 bar, vx5 bar, vx6, and vf on one side, and the other's vertex on the other side. The cut cuts through any hyperedge that represents a satisfied course. So the result also implies that any SAT formula phi, which may have exponential many courses, can be compressed into a representation of size order n squared, such that for any assignment, we can recover the number of courses satisfied to within a factor of 1 plus or minus epsilon. In the rest of the talk, we will review the technicals and main difficulties in the previous works and the new idea to break through them. Throughout the talk, we will focus on unweighted hypergraphs, and the results could be easily generalized to weighted hypergraphs. We first review the definition of edge strengths. A k-strong component of a graph G is a maximal vertex-induced subgraph of G that has minimum cut size at least k. The strength of an edge E, denoted by ke, is the maximum value k that E is contained in a k-strong component. It is a well-known result that the sum of weight over strength over all edges is at most n-1 for any graph. Note that the definition of strength and the upper bound on the sum of weight over strength also holds for hypergraphs. Benzo and Kaga proves that for any graph G, if we sample each edge E with probability Pe equals a large constant times log n over epsilon squared times ke, and give weight We equals 1 over Pe if it gets sampled, then the resulting graph G prime is an epsilon cut sparsifier of G with order n log n edges. In order to prove this result, there is an important intermediate result called cut counting bound, which says that given a graph G with minimum cut size C, the number of cuts in G with size at most alpha C is at most n to the 2 alpha, which means that for any constant alpha, the number of cut size of alpha C is polynomial, which allows us using a union bound on the cuts, since the larger the cut, the more concentration on the cut size we get. Koga and Cross-Gamma generalized the cut counting bound to hypergraph, which says that for any hypergraph edge with minimum cut size C, for any constant alpha, the number of cuts in H with size at most alpha C is at most 2 to the 2 alpha R times n to the 2 alpha, which is equals to 2 to the 2 alpha times R plus log n. As a result, they prove that for any hypergraph H, if we sample each hyperedge E with probability C times R plus log n over epsilon squared times ke, where C is a large constant, and give weight We equals 1 over P if it gets sampled, then the resulting graph is a epsilon cut sparsifier of H. It will have order n times R plus log n over epsilon squared hyperedges. So in order to improve the result, we might want to improve the cut counting bound. However, the cut counting bound in hypergraph is tight. Consider this sunflower-like graph. There is a vertex in the middle, and R-1 unique vertices in each petal, and there are about n over R petals at all. In each petal, there are R squared over 4 parallel edges that contains all R vertices, and there is also a R clique. The mean cut size of this hypergraph is R squared plus R-1, and any cut that cuts through alpha petals has size at most alpha times R squared over 2, which is smaller than 2 times alpha C, and there are n over R choose alpha times 2 to the alpha R such cuts, which is close to the cut counting bound. However, Since each edge in this graph has strength about r squared, even we set PE equals to order r over KE, the total number of hyperedges get sampled is order n, as there are only r squared edges in each petal and nr edges in total. So when we ask that if the sum of 1 over k is smaller than n-1 bound is not tight when r is large. But this is also not the case. Consider this example. It is similar to the previous one, except that there are only r parallel edges in each petal. Now each edge has strength about 2r-1 in this graph. If each edge is sampled with probability r over ke, the size of the sampled graph will be omega n times r. However, the number of cuts of size alpha c is only n choose alpha, which is far from the cut counting bound. And if we set PE equals 1 over KE, we will still get a valid epsilon cut sparsifier. Let's put these two examples together. For the graph on the left, the number of small cuts is close to cut counting bound. If we set PE equals 1 over KE, it does not give a valid sparsifier. On the other hand, the sum of 1 over k is close to n over r, which is far from n. While for the graph on the right, the number of small cuts is far from the cut counting bound, and setting PE equals 1 over ke gives a valid sparsifier, and the sum of 1 over k is close to n. Although these two graphs both have a cut sparsifier with order and edges, but the relationship of sample ratio and the strength are very different. So the strength of a hyperedge might not be the right thing to look at, or at least it is not enough. Notice that in the left graph, for most of the cut, the hyperedges with size r makes up at least a constant fraction of the size of the cut, while on the right graph, for most of the cut, most of the size is given by a normal edge, which has size 2. So we may want to find a way to make the hyperedges have same size. The idea is to convert each hyperedge to a clique, and distributing its weight uniformly to the edges. For any hyperedge E, we call the clique associated with the hyperedge FE. We will refer the resulting graph as the auxiliary graph associated with the hypergraph. Note that although we focus on unweighted hypergraph, the auxiliary graph has weighted edges. We then compute the strength of each edge in auxiliary graph. For each hyperedge E, set P equals order sum of WF over KF over all F in FE. By this way, the total number of hyperedges get sampled is the sum of WF over PF over all edge in the auxiliary graph, which is order n. But do we preserve all cut value by sampling the hyperedges in this way? The idea at least works on both examples we previously saw. In both graphs, as all edges coming from hyperedge has about 1 over r squared weight, the total weight of parallel edges in each edge slot is constant, so the strength of each edge in auxiliary graph is about r in both graphs, and the sample rate of the edges in both hypergraph is about 1 over r, which is about r over ke in the left graph and about 1 over ke in the right graph. However, there is a counterexample where this method does not work. In this example, we have two sets of vertices. There are n over 2 choose r hyperedges of size r in each set, and there are also two edges E1 contains r-1 vertices in the first set and one vertex in the second set. E2 contains r over 2 vertices in both sets. Since any cut cuts through any one set has exponential size, the only small cut is the cut that splits these two sets in the middle, which is constant in the auxiliary graph. So the probability of PE would be about 1 over r, as there are only about r edges has small strength. So with some probability 1 minus order of 1 over r, the cut size in the middle would be 1 in the sampled graph, which means the cut size will not be preserved because the cut size in the original graph is 2. Notice that the strength of edges in cliques representing hyperedges are very different. As a result, E1 and E2 are treated very differently, which leads to the problem. So we modify the idea as follows. We assign weights to the edges in each FE so that the sum of weights is still 1, and make the strength of edges in each clique similar. Then we set PE equals the strengths of the edges in the clique FE, which are similar to each other. By doing so, we have sum of the PE equals the sum of WF over KF on all edge F, which is order n. However, note that some edges in the clique might always have much larger strength than the other edges. For example, the edges in each dense set in the example always have exponential strength and much larger than the strength of the edges crossing the middle cut. But if we set WF equals 0 for these edges, then these edges won't contribute to PE. This idea works on this example, as we will assign 1 over R weight on each edge across in the middle cut in E1, and by doing so, both PE1 and PE2 are constant, and the cut size will be preserved. We formalize the idea as follows. For each hyperedge E, we set kappa E be the smallest strength of edges in FE, and kappa max E be the maximum strength of positive weight edge in FE. We call a weight assignment of the auxiliary graph is a balanced weight assignment if for each hyperedge E, the total weight of all edges in each FE is 1, and kappa max E over kappa E is at most 2, and we set PE equals C times log n over epsilon squared times kappa E, where C is a large constant. To prove the result, we have 2 tasks. Due to the time limit, they won't be covered in this talk. The first task is to prove that balanced assignments always exist, and we can find one in polynomial time. The proof is quite involved, and in fact we can prove that there exists assignments that for each E, kappa E and kappa max E are the same, although such an assignment might not be able to find in polynomial time. The second task is to prove that any balanced weight assignment gives a valid cut sparsifier. This path follows by modifying the framework of Benzo and Kagler. This concludes the main idea of this work. There are several possible directions in the future. First of all, although the number of hyperedges in Cut Sparsifier in this work is tight within a logarithm factor, it is still possible that there is a data structure that preserves every cut in hypergraph using smaller of n squared bits. Also, can we give a better hypergraph spectral sparsifier? Currently, the best non-hypergraph spectral sparsifiers have order n cube or order n times r cube hyperedges. Thanks for listening.